You enter the Ram Yantra through this from the north direction. This is the only way in into the instrument, and once you enter the instrument, well, you hit a dead end when you reach the central gnomon here. So to reach these other segments, either one climbs up onto the floor segments or goes through these. And it is better to avoid actually climbing up to the floor segments because they have markings on them. So it's quite a backbreaking exercise actually to be doing observations with the Ram Yantra. But we had done this with all the public visitors and students who had come in March 2004 when we measured the maximum elongation of Venus using the Ram Yantra, and it was quite an exhilarating exercise, if backbreaking. Well, this is the central gnomon, which whose height is supposed to be equal to the inner radial length and the heights of these walls. So here we have a number of amateur astronomers who are making the inner radial length measurements for all the floor sectors of the Ram Yantra when we were preparing a report to be submitted to the Archaeological Survey of India. And so what happens is that one looks at the shadow of this gnomon wall falling either on the wall sectors or the floor sectors. If the shadow falls in the gap, then one has to move to the other Ram Yantra. And this is the shadow of this thick gnomon, and there is a curvature to this, and by bringing a stretch string, taut stretch string, to tangentially cut this curvature, one can actually find out the edge of the shadow, and that marks the location of the sun shadow and the position of the sun in the sky. The altitude is in the radial direction, so because this is equal to this and equal to this, when the altitude of the sun, let's say in the sky, is equal to 45 degrees, this shadow will touch the junction between the wall and the floor. When the altitude is 0, it will be here, and when the altitude is 90 degree, it will touch the gnomon. Of course, sun is never at 90 degree altitude from Delhi, but 90 degree altitude is measured here. So anywhere along here, and then the original markings on this read off 1 degree each along this. Currently there are no markings, so the way we measure the altitude then is to measure the entire length of these, and of course average length of all these floor sectors we take equal to the length of the gnomon, height of the gnomon, and so just use the length to the shadow and the entire length, and use basic simple trigonometry to measure the altitudes of objects, and quite interesting results in terms of this were obtained over the time by many students. Nighttime observations can be done. That's actually the moon just against the gnomon. One has to view an object keeping one's eye inside these gap regions actually, and make it just come against the central part of the gnomon, and then by measuring the position in the cylinder where our eye is, one can actually measure the altitude and the azimuth along this sector. The azimuth is just circumferential direction. There are 30 floor sectors and there are 30 gaps. So all in all 60, each of them is 6 degrees in azimuth. So starting from the point north and going in this direction, one can measure the azimuth. What happens is that there has to be a 180 degree offset to this because the object might be one place and the shadow will be in the other direction. So the altitude and azimuth of any celestial object can be measured very simply with this instrument and remarkably accurately for educational purposes.